Hello class, Professor Anderson here. Let's talk about torque. Okay, torque is one of these words that I'm sure you've heard many times, perhaps in reference to automobile engines and car performance. You know, they talk about the horsepower of the car, but they also talk about the torque. Okay, you've also probably thought, oh, I really torqued my neck, right? What do you mean when you say that word torque? Well, torque is intimately connected to this idea of rotation. You're twisting something, you're causing it to rotate. So when they talk about the torque of an automobile, they're talking about the ability of the engine to rotate the wheels ultimately. If you think about the torque of a sports car, it's actually pretty low compared to the torque of a tractor. Okay, a tractor is able to turn those wheels even in solid mud, whereas a sports car can't, maybe. Now, a sports car obviously has a much higher top speed than a tractor, but it's a different concept that has to do with horsepower and with aerodynamics. So, torque is about twisting. It's about rotating things. So let's think about the following example. Let's say you want to open a door. Okay, you can't wait to get out of my class. You're trying to push out through the door. Here is the door. Okay, this is a top view of the door. And when you go out, you want to open that door, and you want to open it as easily as possible. So where should you push on the door? Should you push here, or should you push there? Well, you've all experienced this problem. If you push on the wrong side of the door doesn't open because you need to know where the hinges are. Okay? So if the hinges are right there, then clearly you don't want to push where the hinge is. You want to push on the opposite side. That's the easiest way to open the door. Now, a lot of doors, you don't know where the hinge is, right? The hinges are invisible. And so the only way to be totally sure that you're going to open the door and not make a fool of yourself is to push right in the middle. Okay? That's not going to be as easy as pushing on the end away from the hinge, but it saves you the embarrassment of walking into the door and not being able to open it at all. Okay, so this is the idea with torque. Torque is in fact what opens the door here. So let's think about this for a second. Torque, tau, is defined as RF sine of phi. Now, what does all that mean? Well, if I have a door, and that door is length r, and there's our axis of rotation right there. That's where the hinge is. And I push on the door with a force F, and I make an angle phi with respect to the door, then the torque that I apply is exactly this, RF sine of phi. All right, what does that mean, RF sine of phi? Well, let's think about that triangle for a second where that F is. Let's blow this up a little bit bigger, okay? So here's our door. Here is our force F. And we applied the force in that direction. And this was angle phi. Now, this is a vector, of course, and a vector I can write as the sum of two vectors. I could write this one, which we will call F perpendicular, meaning perpendicular to the door, and this one, which we will call F parallel, parallel to the door. So if the torque is equal to RF sine phi, isn't that exactly the same as RF perpendicular? Because look, I made a right triangle here. This is a right angle. So this F perpendicular is the sine component of that triangle, right? This is the angle here. Sine is opposite over hypotenuse. So F perpendicular is in fact just F sine phi. Okay, so what's torque? Torque is equal to R F perpendicular. And what we mean by that F perpendicular is perpendicular to the door. What is the component of F that is perpendicular to the door? Okay. Let's talk about some conventions for torque. The way we typically define torque is the following. If this is counterclockwise, then that is a positive torque. Clockwise is therefore a negative torque. So if you're trying to rotate counterclockwise, we typically call that positive torque. If you're trying to rotate clockwise, that's typically called negative torque. All right, so let's go back to the problem of our door for a second, and let's see what happens when we push with F at the end of the door, and we'll say the door is length D. Actually, what do we use? We used R, so let's keep it as R. Okay. The torque on the door is going to be R times F times the sine of phi, or RF perpendicular. Now, if I am pushing on the door at a right angle to the door, I am already perpendicular. So in this case, torque is just equal to R times F, and it's trying to rotate that door counterclockwise, and so we say it has a positive torque. But now let's say the following. You're trying to leave the classroom, and somebody else is trying to come into the classroom. So here's our door. You push with force F, but somebody else is trying to come in, and they are pushing with force F, but they're pushing in the middle of the door because they don't know where the hinges are. Let's say that they are exactly in the middle of the door at R/2. What is the torque on the door, and who's going to win? All right, so we want the net torque. The net torque, we just add up all the torques. And what we said was if it is counterclockwise, it is a positive number. So this whole length is R. And therefore, the torque that you exert is R times F. The torque that the other person exerts is R times F/2. Well, it's R/2 times F. And we are negative in that case because it's trying to rotate it clockwise. And so look what happens. You just end up with 1/2 RF. It's still a positive number, and so in fact you will win. The person pushing on this part of the door will be able to open it against the torque from the other person. Okay, so that's hopefully clear. If not, come see me in my office. Cheers.